That was a long, hard clip. We learned a lot. And there's more. One last edition of physics before we turn our attention back to astronomy, and we'll be equipped for most of the class, though we will have occasion to introduce more science. There is a lot to discover. So we're back to our understanding of light, which, as I said, is extremely important to us. And the first thing we want to consider are the possibilities for what happens when light meets matter. So we talked about dense objects like the Earth. When light hits the Earth, most of the light is absorbed. We know you shine a flashlight at the ground, it doesn't go through. Objects as dense as Earth take up only a very small fraction of space, but there are, in fact, large, cold clouds of dust and gas that absorb radiation, so they look very dark. So there is the possibility that dense enough and cold enough objects simply absorb light, or some of the light might be reflected when you shine a flashlight beam on the ground. Some of it bounces up. If you put your hand above the beam, you will see light coming off your hand. So we can get some reflection off of dense objects, and that in fact is how we see the world around us. Sunlight bounces off dense things, and we see them and don't walk into them. Now, in general, how much is absorbed can depend on the wavelength. So different materials reflect different amounts of the light in different wavelengths. This is how dyes and colors work. So the sweatshirt I am wearing is red because someone imbibed the fibers with a dye that absorbs, say, green light, and that makes the light that it emits look this nice dark red color. And other things, the walls behind me are painted with a paint that reflects mostly blue light, and therefore they look blue. And so what that means is that as we look around the universe and we see colors of things, sometimes if you see the colors of reflected light, you can conclude something about the chemical composition of the thing you're looking at. There is another interaction of light with matter that will be of great importance to us, and as we'll see, will explain interesting things, and that is the possibility that if you have matter that is not dense, that is tenuous enough to be transparent, so most of the light goes through, light scatters off of molecules, atoms, dust grains, anything, really. And the mathematical formulation was given by Lord Rayleigh in 1871, so it's called Rayleigh scattering. And what scattering means that a light beam coming in will hit some particle and be deflected at some angle. What that means is that you, looking here, will see light coming from over there that actually came from over there. You will see light coming from the wrong direction. Now, this phenomenon decreases with wavelength. Long wavelengths scatter far less than short wavelengths. So blue light scatters more than red. If you recall this image of the Pleiades cluster M45, we saw this blue wispy light all around. This is scattered light. These are clouds of dust around these stars, and the starlight is scattering off of them, so that light from this star that was not supposed to hit us on Earth, that was heading somewhere else, got scattered by dust over here, and so we are seeing light, starlight, coming from the wrong direction because it was scattered by the dust. This has lots of interesting consequences, and one of my favorite is the following. In this experiment, we're going to simulate the interaction of sunlight with the atmosphere, and we'll learn some things. On the left-hand side, we see the apparatus. We have a cup of water standing on an overhead projector. The overhead projector has a round hole cut in a mask, and so what we see is we see the cup of water, and we see the light going through the cup of water and projected onto the wall. Water is transparent, and so looking through the cup and seeing the dark color, we're seeing the darkness of the curtains beyond it, just as were the air completely transparent, we would look above us and see the darkness of space. Indeed, if our Earth's atmosphere were completely clear, then, looking at the sun, we would see the bright white color of a black body object with a peak somewhere in the visible, The peak is broad enough that there's no distinguishable difference between the way our various receptors are excited. So any object with a black body spectrum of a few thousand degrees, like an incandescent light bulb, will appear bright white to us, as would the sun. The rest of the sky, though, when we're looking away from the sun, would appear dark. And this famous Apollo image that we see of Earthrise over the lunar surface is a great example of this. Clearly it is daytime on the moon. From the phase of the Earth, you can tell that the sun is directly overhead, as seen by the astronauts on the moon at this point. And you can see that the moon's surface is brightly lit, the sun is overhead, and yet the sky on the moon is completely dark. Had we looked at the sun, we would see a bright white sun. Looking away from the sun, the sky is dark, and in fact you can see stars in the daytime. This is not the situation on Earth, and the difference between the moon and the Earth is our atmosphere. To simulate 100 miles of air overhead with its abundance of scattering opportunities for incoming light, what I have done is I have stirred some reagents into this cup. Over time, as they react, they will precipitate increasingly large concentrations of small crumbs of sulfur into the water. These will serve as scattering centers and will allow us to emulate 100 miles of atmosphere in 6 inches. And what we're going to do is, as the concentration of sulfur increases, we will follow on the left-hand side what the cup looks like. This emulates what you'd see in the sky looking away from the sun, which right now is a dark sky and presumably star-studded. And on the right, we'll see what happens when you look directly at the light source. This will simulate what you would see looking directly at the sun. We've now achieved a sufficient concentration of sulfur precipitate that there's a lot of scattering going on in that cup, and the water is no longer transparent. In fact, we don't see the dark curtains through it. We see that it's glowing, and as predicted, blue light scatters more than any other color. So the color this cup is glowing is a bright sky blue, and as the precipitate continues to increase in concentration, that glow will get brighter and brighter. What we are seeing is sunlight scattered off the scattering centers in the sky, water molecules, dust particles, air molecules themselves, causing the sky to glow blue when you're looking away from the sun. And this is a very dramatic demonstration of what it is we're seeing. Looking on the right, we see what has happened to the transmitted sunlight. This is, remember, what you see when you look straight at the sun. Some of the blue light that would have reached your eyes had it not been scattered has been scattered in other directions in interactions with the atmosphere. This leaves the sunlight that reaches your eyes blue depleted, and blue depleted white light, you recall, looks to our eyes yellow. It's a combination of green and red with smaller amounts of blue. What we perceive that is as yellow light. This is the reason the sun looks yellow. We've now achieved a high enough concentration of scatterers that in fact when we look at the cup, it not only glows very brightly, but it in fact appears white. We see all colors of the light scattered towards our eyes. This is somewhat the color of a bright white cloud in the sky. A cloud contains many ice crystals. Light is reflected and scattered off of the ice. We see all colors reflected from a white cloud, so that's the reason we're seeing this. But we still have, as you can see at the edges where the camera is less saturated, there is still a preponderance of blue light in the scattered light, and this is very dramatically evident on the right when we see that the transmitted sunlight is now really a dark yellow. As the light loses blue components to scattering, what's left is a yellow that is somewhat reminiscent of the color of the sun as we see it. We also see that as more and more of the light gets scattered, the observed sunlight is dimmer. Indeed, the atmosphere dims the sun by distributing some of its light in all kinds of other directions. The sun is much brighter on the moon where there's no atmosphere. Finally, having waited for the concentration of scatterers in the cup to increase to the point where, as you see on the left, the cup glows bright white, you can see that what's going on is that not only have the blue hues of the incoming white light been scattered away, but in fact it's lost much of its green, and the remaining color of the transmitted light, as we see on the right, is darker than yellow. In fact, it's an orange, and as scattering continues to increase, we will lose more and more of the green, and eventually the transmitted sunlight will appear almost red. This might remind you that there are circumstances under which, indeed, the sun in the sky appears red. I hope you found that demo as fascinating as I always do. What did we see? We saw that the atmosphere scatters blue light in preference over other colors, making the sky glow blue, and because of depletion of blue light, the sun appears yellow, so light of all colors impinges on the atmosphere, and the blue light scatters, so that if we look away from the sun over here, we see blue light scattered in our direction, among others, from the sunlight that hit over here, but the rays that penetrate are the greens and the reds. Together, blue depleted white light appears to us to be blue. And then, as we increase the concentration of scatterers, effectively making the atmosphere contain more impurities or be thicker, we saw when we got more scattering, we lost the green as well as the blue, and that left the sun looking distinctly red. And of course, the sun looks red to us at sunrise and sunset when it's low in the sky. The reason for this is both because at sunrise and sunset we're looking not through 100 kilometers of atmosphere, but through a few thousand kilometers of atmosphere. And moreover, most of the impurities in the atmosphere, the big scatterers, are at low altitudes, and the grazing rays of the rising or setting sun have more opportunity to encounter them and scatter. And so the blue scatters early, then the greens, then the yellows, and so on. And only at the end of the day, red light penetrates all the way through to our eyes. So that same demo shows us why the sky is blue, why the sun looks yellow, and why sunsets are red. Now, I can't resist a few other brilliant examples of scattering on Earth. One is crystals of ice, because of their geometry, tend to scatter light preferentially at particular angles. There are many forms of ice crystals. One hexagonal form that forms in high altitude clouds tends to scatter light at an angle of 22 degrees, and so you very often see at night the moon with a 22-degree ring around it. So again, this is moonlight that was not aimed at you, but at someone 22 degrees away from you, was deflected and is hitting you. And so you see this beautiful ring around the moon. You can get a ring around the sun, but the sun is too brilliant. On the other hand, the geometry of water droplets and the optical properties of water say that water droplets like to scatter light through an angle of 140 degrees approximately. What this means is that the light is returning in the direction of the sun, and it forms a big circle with a radius of 40 degrees around the direction diametrically opposed to the sun. And so if the sun is high in the sky, this is typically below you and you don't see anything. But if the sun is low, you can see parts of a big circle in the sky in the direction opposite the direction of the sun. And because the light has gone through water and the optical properties of water depend on the wavelength, different colors of light get deflected by slightly different angles, and we get the brilliant phenomenon of the rainbow. And as I said, the best rainbows are always early in the morning or late in the afternoon. The sun is low and the rainbow therefore high. If you want to see a rainbow at midday with the sun overhead, you have to be able to be looking down at the clouds, as this paraglider pilot is doing. The round rainbow, in this case double, with the shadow of your glider in the middle, is called a glory, and it is indeed a glorious sight. The sun, as we know, has a blackbody spectrum. It's a blackbody with a temperature of 6,000 degrees, and it looks white. In general, the blackbody spectrum is sufficiently broad that anything with a temperature of a few thousand degrees, the sun, an incandescent lamp, such that the maximum is anywhere near the visible, will not create sufficient differences between the way it activates our green, blue, and red receptors to give us a great sensation of color. So the sun appears to us white. Remember, its wavelength of maximum emission is right smack in the middle of the visible spectrum in the green, and it makes a beautiful rainbow of colors. And here someone has laid out the solar spectrum line by line by line, so this is to be read like a book. It's a very detailed spectrum of the sun, and indeed there's a blackbody spectrum here centered on the green, but there are these gaps, there are holes, there are specific wavelengths along the spectrum in which there are holes. Something is eating. The blackbody spectrum is continuous. Something is absorbing the light at particular wavelengths. And this was a discovery by Fraunhofer in 1814. And a few years later, Kirchhoff and Bunsen discover that if you heat a tenuous gas, a gas under low pressure and very low density, then the gas will glow if you either heat it by burning or ionize it by passing a current through it, when the gas is sufficiently tenuous, the light that it glows with is actually not black body spectrum, but only discrete spectral lines. And Kirchhoff is the one who figured out the regularity that relates these two pictures, and let's see how that works. We have incandescent light here, or if you want any black body, say a star, and like the sun. If you are looking at this star, then you will just see in your spectrometer a continuous black body spectrum with the maximum emission determined by the temperature of the star. To the left is a cloud of tenuous gas, so low pressure, low density, and if you observe the emissions from that cloud of tenuous gas, you get this line spectrum that Kirchhoff and Bunsen discovered. There will be discrete wavelengths, discrete places. It's called a line spectrum for the obvious reason of its appearance. There will be discrete places in the spectrum where this cloud will emit. On the other hand, if you observe the continuous emitter, the black body, through the cloud, you will see the rainbow, the full continuous black body spectrum of the black body that's behind, and at precisely the same wavelengths where you saw emission, you will see absorption. In other words, an atom or a molecule is characterized by a specific set of wavelengths at which it can either emit light or absorb. Now, when you bunch a whole collection of atoms densely together, then these lines are broadened gradually as you increase the density, and eventually when the density becomes large enough, they merge into the continuous spectrum of a black body that absorbs all light at any wavelength and emits in a continuous black body spectrum. But if the density is low and the pressure is low enough, then you find discrete emission as well as discrete absorption. So these wavelengths are properties of the gases in the cloud that we're talking about. Naturally, this discovery was a huge boon to chemistry, because what it allowed Kirchhoff and Bunsen to do was to heat various gases, observe the emission line spectrum, and conclude, identify the wavelengths of emission with those from known atoms, known elements, and they could find the elementary composition, the chemical composition of the substance that they were observing. Thus was born the field of spectroscopy. And so as we've seen, observing the line spectrum allows you to identify. So you can go over, or an expert can go over the spectrum and identify that this line, and that line correspond to the wavelengths at which we know thrice ionized iron atoms absorb radiation. So the degree, the darkness of these lines, the amount of absorption indicates something about the concentration of thrice ionized iron, and so on and so forth. You can go through the solar spectrum and identify all the elements that are there. And then in 1868, an interesting discovery is made by Janssen and Lockyer. Independently, they look at the spectrum of sunlight during an eclipse, and they discover a line in the yellow right over here in this region of the spectrum, and it does not correspond to any known element. And so, after some further checks, they decide that they have discovered a brand new unknown element, and since it was discovered in the spectrum of the sun, they name it appropriately helium. The helium you put in your birthday balloons was first discovered to exist in the spectrum of the sun. We'll talk later about why it's so hard to find helium on Earth. But the first indications of the existence of such a substance were in the spectrum of the sun. So observing the line spectrum of an astronomical object will tell us about its chemical composition, and as we shall see, a whole lot more. So spectra will be with us for a good part of the class. Understanding why particular atoms emitted at particular wavelengths was an interesting problem, but before that could be solved, a revolution in our understanding of the structure of the atom had emerged. By this time, J.J. Thomson had discovered that one of the constituents of matter was something he called electrons. They were responsible for the conduction of electricity and metal, hence the name, and they were negatively charged. And one suspected that an atom, being electrically neutral, would have some positive charge and some electrons. And indeed, Rutherford, in 1909, sets out to discover this structure with his students Geiger and Marsden. And what he discovers is astonishing. He discovers that most of the mass of the atom is contained in a positive nucleus whose size is of the order of 10 to the minus 15 meters. For the sake of comparison, the size of an atom is on the order of 10 to the minus 10 meters, so angstroms. So only 100,000th of the radius of an atom, remember you have to cube this to get the volume, is taken up by most of the mass. So there's a very tiny, very heavy, very compact nucleus, and it's surrounded, Rutherford understands, by electrons. The charge of the nucleus is the atomic number of the element, depending on the atom, and there are a corresponding number of negatively charged electrons, so the whole thing is neutral. And what Rutherford concludes is that the electrons are essentially orbiting the nucleus in Keplerian orbits, which is what gives this large size with the mass concentrated very tightly in the middle. This is a beautiful example of universality. The force law between electrons and protons is Coulomb's law. It's quadratic. You get exactly the same elliptical orbits that you see in the solar system. And so this is the picture of the atom that we're so familiar with. And then once we understand this, then atoms can bind chemically by trading, sharing electrons, or deforming the distribution of their electron orbits. The development of chemistry from this point is very quick, and chemistry is the science of electronic rearrangement. What we understand now is why it is that elements are immutable. The number of carbon atoms that goes into a reaction is always equal to the number of carbon atoms that emerge, and that is because the nucleus is not affected. A carbon nucleus specifies that this is going to be a carbon atom because it has the right charge. Set it out somewhere and it will acquire electrons until it is neutral. So a nucleus identifies the chemical structure of the element. And because the nucleus does not participate in these electronic rearrangement issues, elements are immutable, and the project of alchemy of converting the element gold into the element lead or the other way around is completely hopeless. Now, this is a brilliant and successful picture of the world. And Newton's universe is becoming richer and at the same time better understood. And there are those who speculate at the end of the 19th century that physics is all but resolved, but there are a few niggling problems. One of them that we can understand is this issue of atoms. So imagine the simplest of all atoms, a hydrogen atom. It has a nucleus with charge 1 and 1 electron orbiting it. This electron is in motion and in fact is accelerating. It's moving in a circle. And an accelerating charge will create changing electric and magnetic fields. This means it will create radiation. The radiation will carry off energy. The electron will lose energy. And as we know, you have some particular amount of energy determines your orbit. As you lose energy, you fall to lower and lower orbits. So what you expect the electron to do is to spiral in towards the nucleus while continuously emitting radiation. Atoms obviously are observed to be stable, and the stability of the atom is a big riddle. Similarly, why is it that atoms only emit at discrete frequencies? You can easily imagine that an electron revolving around an atom would radiate at the frequency. The periodic nature of the radiation would be related to the periodic nature of the motion. But Keplerian orbits, as we know, exist at any radius, and given a radius, you can figure out the frequency from p squared equals ka cubed. And so, since you can orbit at any radius, you can orbit at any frequency, and therefore you would expect atoms to be able to emit radiation at all wavelengths. What is this discrete line spectrum? And then there are some experimental puzzles. These are sort of theoretical thought puzzles. There are experimental situations in which light is observed to have particle-like behavior. Remember, Newton said light was a particle, and it was one of the rare times he was wrong, but not quite. And so this is first conjectured by Planck in 1900 to explain some details of the shape of a black body spectrum, and then by Einstein in 1905 to explain something called the photoelectric effect. And the picture that emerges is that a beam of light can be thought of, under some circumstances, as a stream of particles. And if the light wave has frequency f, then each of those particles carries an energy which is proportional to the frequency f, and the constant of proportionality, this object h, is known as Planck's constant, and it has units, of course, of energy per frequency, or energy times time, and it is a very small amount of energy times time. So h is a very small number. It means that a beam with a non-trivial flux of energy contains huge numbers of these photons, as these light particles are called. And because there are so many of them, the fact that at any given moment a particle is or isn't impinging on a detector doesn't happen. But if you have a beam of very low power, then this quantization, as Einstein calls it, the fact that the energy of a beam is carried in discrete packets, might become apparent. And to complicate things, so we have this object that has been observed to be a wave, because Young showed that light undergoes interference, exhibiting some particle properties. And then in 1927, Davison and Germer in the US do an experiment in which they basically observe that electrons exhibit interference. Electrons, manifestly particles, exhibit some of the properties that we said were the hallmark of wave behavior. So there's this weird duality emerging between waves and particles. What is a particle sometimes behaves like a wave sometimes behaves like a collection of particles. And all of this is resolved over the course of the teens and 20s of the 20th century by a beautiful and to this day somewhat puzzling theory called quantum mechanics, which leads to a complete revolution in our understanding of nature. This is the first time that we go way beyond anything Newton could have imagined, let alone written down. And this is modern physics, as we call it, 20th century physics. And in quantum mechanics, particles, all the states of a particle, rather than being described by their positions and velocities, are described by something called a wave function. And this wave function has the property that its value at any position in space at any given time predicts the probability of finding the particle, the probability density technically, of finding the particle at that point in space at that particular time. And notice I said probability and I said state, so the full state of the universe only predicts the probabilities for particles to be here, there, or anywhere else. There are not definitive predictions. It's not that our ignorance prevents us from knowing it. In quantum mechanics, the universe does not know where a particle is, and yet the deterministic evolution that was so satisfactory about Newtonian mechanics is in some deep sense retained here, in the sense that the evolution of the wave function itself is completely deterministic. The results of measurements, however, can only be predicted with probability. Again, when the numbers of particles are on the order of a mole, then the law of large numbers guarantees that these distributions will be very sharply peaked, and the probability that I am not here right now but somewhere else is exceedingly low, and I don't need to worry about it. Now, associated to this, a particle is associated a wave. This wave has a wavelength. The wavelength is determined by the particle's momentum, and again that Planck's constant thing shows up. The wavelength is related to the momentum by this relation lambda is h over p. So again, h is a very microscopic number. Macroscopic values of momenta lead to negligible wavelengths, and therefore the wave behavior of a macroscopic object is completely negligible, and you won't see it. Only at microscopic distance scales can you observe real quantum behavior. Now, we won't have time to discuss either the nature of this beautiful theory, sadly, or all of its consequences, but a few that are important to us. First, I said this resolves the issue of the discrete spectrum. Indeed, solving the equation for this wave function for electrons in an atom, you find that electrons can only occupy a discrete set of energy levels. The energy of an electron can be, in an atom, can be one of a few discrete values, and in a hydrogen atom, for example, this is the form that these energy levels take. K is some constant, and the energies are, of course, negative. These are all bound states. And the energy levels are some constant divided by n squared, where n can be 1, 2, etc. So 1 is the lowest energy, and as n gets bigger, you get states with larger and larger energies tending to 0 as n becomes large. And the point is that the dominant interaction between an atom and radiation is the emission or absorption of a single photon. One atom emits one photon, one light particle, and at the same time, the electron jumps, undergoes what we call a quantum transition between energy levels. And then energy conservation guarantees that, for example, if a photon is emitted while jumping from level n to level m, in which case the energy n must be bigger than m, then energy conservation says the energy taken away by the photon, which is hf, is the difference between the initial and final energy. The energy lost by the atom is equal to the energy taken away by the photon, and plugging in our value, we get this answer. And indeed, these frequencies, you can convert them to wavelengths, are observed in the spectrum of the hydrogen atom, for example. And so the discrete energy levels are very nicely explained by this, and many other phenomena are explained. As one outcome of this that is very crucially important to us is the Pauli exclusion principle. Pauli exclusion principle states that electrons are a kind of particle later termed fermions, and it tells us that at most 2 electrons can occupy a given energy level or a given state. And for those who like to think about these things, electrons have spin. They can have 2 different spin states. 1 electron can actually occupy a given state, but that state information includes which of the 2 spin states it's in. The fact that electrons cannot be compressed and you cannot have more than 1 electron in a given state explains many things. It explains the structure of the periodic table and all the regularities that Mendeleev had found in the chemistry of elements in similar positions in the periodic table are explained by understanding the structure of energy levels and pairing it with this Pauli exclusion principle. It also explains why when I slam the table with my hand doesn't go through the table. Remember that my hand is mostly empty space. Each atom of my hand is mostly empty space, so it's not that there's really literally a collision between atoms. What's really going on is that both in my hand and in the table, all the low-lying energy levels are filled. In order to take a mole of electrons from my hand and mix them into a mole of electrons that are the local part of the table, you need to excite a mole of electrons to slightly higher energy levels that are not yet occupied. Per electron, that's not a lot of energy, but a mole is 10 to the 23 electrons is a lot of electrons. It takes a lot of energy to excite so many electrons to the next energy level. And if I hit the table hard enough to generate enough energy to excite a mole of electrons to the requisite energy level, then I've exerted so much energy that either the chemical bonds in my hand or in the table will break, and one of the 2 objects will just fall apart rather than moving right through each other. So this Pauli exclusion principle explains much of our day-to-day experience. It'll also become very important in understanding some phenomena in astrophysics. Phew! That was a busy week. We have found a ton of new science, and we've come a long way since Newton, not to mention Aristotle. There are many phenomena both on Earth and off of it that we understand, and the main tool that allows us to be so insightful is that atoms are fundamentally the same wherever you go. The behavior of a hydrogen atom on Earth, right here, is indistinguishable from the behavior of a hydrogen atom out in the Crab Nebula or inside the Sun. There may be physical circumstances that are different in the Sun, but if we can emulate those circumstances, hydrogen atoms are hydrogen atoms, helium atoms are helium atoms. The laws of physics are the same here, there, and everywhere, and so these laws that we've discovered by measuring things in labs on Earth can be and are applied to the way things behave in the heavens. Remember, we said that we were going to do Aristotle one better by looking for laws that are valid on heavens as they are on Earth, and indeed, these are the laws that we are going to find. There's a satisfaction in understanding all these things, and I hope that you will take away from this discussion a new way of looking at things you see here on Earth But the purpose of this class was to talk about things away from Earth, and we're finally ready. When we come back next week, we will start to take all this amazing new arsenal of tools we've developed and apply it to actual astronomical phenomena. In the meantime, get some good rest. You've certainly earned it.